When you think about a collision, what normally comes to mind? For many people, it will recall two vehicles crashing into each other. Whether watching a TV show of cars crashing while in a race, or seeing the aftermath of an accident on the road, you've probably had some first-hand experience in seeing a type of collision. A couple of different things can happen when two cars collide. They can bounce off each other, or they can stick together. We call these two categories of collisions: elastic and inelastic collisions, respectively. And these categories apply to more than just car crashes. Any collision where two things bounce off one another, like a bowling ball hitting pins, is called an elastic collision. Similarly, any collisions where two things stick together, like one football player tackling another, is considered an inelastic collision. In this lesson, we'll focus on the former and dive into learning about the physics that occur in a one-dimensional elastic collision. While working on collisions in introductory physics courses, what we're really doing is exploring conservation laws. Specifically, we look at how the conservation of momentum and kinetic energy work in a collision. When we say momentum is conserved in an elastic collision, conservation of momentum, in other words, what we really mean is that the total momentum of the two objects colliding is the same before and after the collision. Mathematically, we write this out as follows. Here, P stands for momentum, M for mass, and V for velocity. The subscripts tell us whether we're talking about the total, or TOT, amount of the momentum, the initial, which is I, or final, which is F, momentum or velocity, and the momentum, mass, or velocity of object 1 or object 2. In this way, PITOT is the initial total momentum, VF2 is the final velocity of the second object, and so forth. To see how we use this formula in practice, let's work through an example problem together. When children play a game of marbles, their goal is to roll a large marble at smaller ones and bounce them out of a boundary drawn on the ground. One child rolls their large marble with a mass of 0.005 kilograms at a velocity of 0.6 meters per second. It strikes the stationary marble with a mass of 0.0036 kilograms. After the collision, the large marble continues forward with a velocity of 0.2 meters per second. What is the final velocity of the smaller marble? With the information that we've been given, we know the mass of both marbles, or M1 and M2, their initial velocities, VI1, VI2, and the final velocity of the large marble, VF1. With this information, we have everything we need to find the velocity of the small marble, VF2, using the conservation of momentum. M1 times VI1 plus M2 times VI2 equals M1 times VF1 plus M2 times VF2. 0.005 kilograms times 0.6 meters per second plus 0.0036 kilograms times 0 meters per second equals 0.005 kilograms times 0.2 meters per second plus 0.0036 kilograms times VF2. As you can see, we gave the smaller marble an initial velocity of 0 meters per second. This is because before the collision, it was standing still, meaning it had no velocity. 0.003 kilograms meters per second plus 0 kilograms meters per second equals 0.001 kilograms meters per second plus 0.0036 kilograms times VF2. 0.003 kilogram meters per second equals 0.001 kilogram meters per second plus 0.0036 kilogram times VF2. 0.002 kilograms meters per second equals 0.0036 kilograms times VF2. 0.56 meters per second equals VF2. One big difference between inelastic and elastic collisions is that kinetic energy is only conserved in the latter. In fact, the collision must be perfectly elastic for the conservation of energy to occur. If there's any inelasticity at all, then some energy is lost. When a collision is perfectly elastic, the law of conservation of kinetic energy tells us that the total kinetic energy of the colliding objects is the same before and after the collision. We write this out mathematically much like we did with the conservation of momentum. In these equations, KE stands for kinetic energy, and the rest of the variables and subscripts are the same as they were in the conservation of momentum equations. When comparing this final formula to what we have for the conservation of momentum, you can see they're actually very similar. If we work through an example problem, it would be much like the one in the previous section. But what we can do instead is use the conservation of momentum and kinetic energy together to solve a more complex problem. Two bumper cars at an amusement park drive directly toward each other. The first bumper car has a mass, or M1, of 200 kilograms, and is traveling with an initial velocity, or VI1, of 4 meters per second. The second bumper car has a mass, or M2, of 160 kilograms, and a velocity, VI2, of negative 6 meters per second. Find the final velocities, or VF1, VF2, of both the first and second bumper car. There are quite a few steps involved to solve this problem, so let's work through them one at a time. The first thing you need to do is take the formula for the conservation of kinetic energy and rearrange it so all M1 factors are located on one side of the equation and M2 factors are on the other side. Next, you'll need to factor out your squares on each side of the equation. Once you've got this done, you'll want to switch over to the formula for the conservation of momentum and get the mass factors on either side of the equation just like you did before. You'll then need to divide your factored out equation for the conservation of kinetic energy by your factored out formula for the conservation of momentum. Now we'll rearrange this equation to put VF2 by itself on one side of the equal sign. This equation can now be plugged back into the original formula for the conservation of momentum to solve for VF1. At this point, you'll want to get the VF1 turn itself on one side of the equal sign. At last, we're ready to insert the information from our problem to solve for the first final velocity. Finally, now that we know one of the final velocities, we can plug back its value into the original formula for the conservation of momentum to solve for the second final velocity. M1 times VI1 plus M2 times VI2 equals M1 times VF1 plus M2 times VF2. 200 kilograms times 4 meters per second plus 160 kilograms times negative 6 meters per second equals 200 kilograms times negative 4.89 meters per second plus 160 kilograms times VF2. 800 kilogram meters per second minus 960 kilogram meters per second equals negative 978 kilograms meters per second plus 160 kilograms times VF2. Negative 160 kilograms meters per second equals negative 978 kilograms meters per second plus 160 kilograms times VF2. 818 kilogram meters per second equals 160 kilograms times VF2. 5.11 meters per second equals VF2. When two objects collide, one of two types of collisions can occur. In an elastic collision, objects bounce off each other after colliding. While in an inelastic collision, the objects that collide stick to each other after the collision. When solving one-dimensional collision problems in a physics course, what we're really working with are conservation laws. For an elastic collision, there are two of these conservation laws that apply. The first is the conservation of momentum, and it states that the total momentum before and after the collision must be the same. Unlike the conservation of momentum, the second conservation law applies only to elastic collisions and not inelastic ones. It is the conservation of kinetic energy which tells us that the total kinetic energy must be the same before and after the collision.